Hello all, my name is Dara Lasniak and I am a third-year PhD student at Purdue University. And today I will be presenting results from a laboratory ion irradiation experiment that simulates solar wind space weathering on a carbonaceous asteroid. The term space weathering refers to the gradual physical and compositional alteration of airless planetary regoliths due to exposure to interplanetary space. In general, there are two primary space weathering processes: micrometeoroid bombardment and solar wind irradiation. Both of these processes generate nanometer scale chemical and structural modifications in the uppermost 100 nanometers of regolith grain surfaces. Some examples of these modifications include nanoparticles and vesicles, both of which are shown in the transmission electron microscope image on the right. And the accumulation of these products over time alters the overall spectral signature of a planetary surface, making it difficult to interpret composition from remote sensing data. And this optical effect of space weathering is problematic for missions, which rely heavily on orbital data to answer all of their scientific objectives. Compared to the Moon and silicate-rich asteroids, we know very little about space weathering of carbonaceous bodies. This knowledge gap is especially pertinent to the NASA OSIRIS-REx and JAXA Hayabusa 2 missions, which have collected material from the carbonaceous asteroids Bennu and Ryugu, respectively. The Hayabusa 2 samples have actually already been brought back to Earth, and the OSIRIS-REx samples are currently en route. To prepare for laboratory analyses of these return samples, my research aims to determine how specifically solar wind irradiation alters the microstructure, chemistry, and spectral properties of carbonaceous materials that contain both organic and silicate phases. To accomplish this goal, we simulated natural solar wind irradiation in the lab using a 5 Versaprobe 3 ion gun. We bombarded two separate regions of a slab of the Murchison carbonaceous chondrite, one with 1 keV hydrogen ions and the other with 4 keV helium ions, to simulate bulk solar wind and isolate the effects of each ion. Although Murchison is not a perfect spectral analog for target asteroids Bennu and Ryugu, it still exhibits important similarities to carbonaceous asteroids, including a low optical albedo and a composition that is rich in organics and phyllosilicates. In terms of experimental conditions, we used a flux of 10 to the 13 ions per centimeter squared per second, and fluences roughly on the order of 10 to the 18 ions per centimeter squared. So for hydrogen irradiation, this simulates an exposure time of around 700 years at Bennu, and for helium irradiation, an exposure time of around 23,000 years at Bennu. So now that we've irradiated our sample, we want to comprehensively analyze it. And for this, we employed coordinated analytical techniques, including X-ray photoelectron spectroscopy, or XPS, to monitor surface chemistry, visible to near infrared spectroscopy, or VNIR, to identify spectral trends, and microprobe two-step laser desorption mass spectrometry, or micro-L2MS, to observe changes in organic functional group chemistry. Finally, we use transmission electron microscopy, or TEM, to identify nanoscale structures and observe elemental distributions. And by using these techniques collectively, we can identify relationships between the spectral, microstructural, and chemical changes induced by ion irradiation. First is XPS analysis, which investigates elemental abundances and chemical states within the approximately outermost 10 nanometers of the sample. The left graph shows survey XPS spectra before and after ion radiation obtained from the matrix regions indicated on the Murchison slab shown in the center. So for the remaining slides, just keep in mind that the black line represents the unirradiated surface, the orange line represents the hydrogen irradiated surface, and then the blue line represents the helium irradiated surface. So the shape of the spectra on the left remained largely the same before and after irradiation. The one major difference is in the surface carbon content. After irradiation, the two carbon peaks, which are indicated by the gray arrows, are removed. Surface carbon abundance decreases by around 90% in the helium irradiated region and around 70% in the hydrogen irradiated region. Now on the right is a graph showing high resolution XPS spectra from the iron 2p region. And this indicates that ion irradiation chemically reduces some ferric and ferrous iron to metallic iron. Next is VNIR analyses. When compared to the unirradiated surface, Absolute reflectance spectra suggest that helium irradiation causes notable brightening and reddening, longward of around 0.65 microns. In contrast, the hydrogen irradiated spectrum is pretty similar to the unirradiated spectrum, with only minor reddening. Now, these trends actually differ from the spectral trends observed in recent micrometeoroid bombardment simulations performed on Murchison by Thompson et al. 2019 and 2020, where laser irradiated surfaces were actually visibly darker than the unirradiated surface. In the continuum removed Wiener spectra, clear diagnostic absorption bands appear, which reflect the composition of the Murchison sample. I specifically want to point out the broad feature between around 0.6 microns and 1.6 microns. This feature is primarily made up of three minima at 0.75, 0.95, and 1.15 microns, all of which are associated with phyllosilicate minerals. However, spectral signatures from both olivine and magnetite could be contributing to this feature as well. Now, the spectral contrast of this broad band weakens in response to both types of ion radiation, with helium causing greater change. While previous ion radiation studies have attributed slope reddening and attenuated absorption bands to the formation of metallic iron nanoparticles, we did not ubiquitously observe nanophase iron in our irradiated Murchison sample during microstructural analyses. Thus, we think that the observed reddening and attenuation may reflect the decomposition of matrix phyllosilicates and the chemical reduction of ferric and ferrous iron to form reduced iron-bearing amorphous material rather than discrete crystalline nanoparticles. Now onto the micro-L2MS analysis, which investigates the abundance and distribution of organic phases. So shown here is a chemical map obtained with the 118 nanometer photoionization laser, which measures nearly all organic free species. For reference, blue regions are low in organics, while red are high. Compared to the unirradiated surface, the helium irradiated map shows decreased organic content, while the hydrogen irradiated map doesn't show much change. However, examination of the summed spectra indicates that hydrogen irradiation actually increases the abundance of some low molecular weight organic species. We think that the higher energy and heavier mass of the helium ions allows them to destroy organics by breaking carbon bonds and sputtering constituent atoms and molecules. Alternatively, hydrogen irradiation likely does not change bulk organic content, but rather breaks apart large macromolecular species, which cannot be detected by the micro-L2MS instrument, into smaller molecular fragments that can be readily detected by micro-L2MS. To prepare for our TEM and energy dispersive X-ray spectroscopy analyses, we extracted 6 focused ion beam cross-sections from our irradiated Murchison sample. These FIB sections were pulled from matrix material, magnesium-rich olivine, and iron-rich olivine in both the helium and hydrogen irradiated regions. And as cross-sections, these FIB sections capture both the surface and interior of our sample, allowing us to evaluate microstructural and compositional differences between the ion-affected surface and the unaltered substrate below. I'm now going to discuss results from our TEM and EDX analyses, moving from the matrix samples to the magnesium-rich olivine samples, and finally the iron-rich olivine samples. But for consistency, the blue and orange color scheme is still used in the remaining slides to differentiate between the FIB sections pulled from the helium irradiated versus the hydrogen irradiated regions. Here is a mosaic of conventional TEM images from our helium irradiated matrix FIB section. There is a continuous, highly vesiculated layer at the surface, which is consistently greater than 100 nanometers in thickness. It is characterized by large vesicles, which are the white blobs in the image, which can reach up to 120 nanometers in length. High-resolution imagery suggests that helium irradiation completely amorphizes phyllosilicates in the matrix up to a depth of around 150 nanometers, which is similar to what was observed by Keller et al. 2015. Another interesting finding in this FIB section is the presence of nanoparticles, which are the bright white specks in this STEM dark field image. These nanoparticles are very small, only around 3 nanometers in diameter at most. They occur mostly below the vesiculated layer and are heterogeneously distributed throughout the sample. So at this moment, we cannot say with certainty if these nanoparticles are in fact derived from ion radiation or if they are intrinsic to the Murchison sample. Our hydrogen-irradiated matrix fib section also has a continuous vesiculated layer at its surface. However, it is thinner compared to the helium-irradiated sample, never exceeding more than 100 nanometers in thickness, and has fewer and smaller vesicles. On the right, you will see a high-resolution image stack showing that amorphization of matrix phyllosilicates extends to a depth of around 60 nanometers. We also didn't find any nanoparticles in this fib section. Our helium-irradiated magnesium-rich olivine fib section has a moderately vesiculated ion-affected region, whose thickness ranges from around 65 to 85 nanometers. It contains both amorphous and polycrystalline olivine, with the proportions of each varying laterally across the sample. Also of note is the relatively silica-enriched and magnesium-depleted, completely amorphous surface layer, which is around 50 nanometers in thickness and can be seen in the EDX map set shown here. Our hydrogen-irradiated magnesium-rich olivine fib section has an ion-affected region that is also moderately vesiculated, ranging from 50 to 85 nanometers thick. Now, this sample is predominantly polycrystalline with few amorphous islands. Polycrystalline regions can occur all the way up to the surface of the fib section, as indicated by the red arrows in this high-resolution TEM image with an inset fast Fourier transform image. Interestingly, our helium-irradiated iron-rich olivine fib section has a highly vesiculated, completely amorphous ion-affected region similar to our matrix samples, which ranges between 120 and 180 nanometers in thickness. The vesicles themselves also vary greatly in size, from a few nanometers to over 100 nanometers in length. This intense vesiculation is also visible on the surface of the sample as a blistered texture in the scanning electron microscope image shown on the left. Matsumoto et al. 2015 observed the same blistered texture in low calcium pyroxene grains returned from the S-type asteroid Itokawa. Now, the fact that this fib section experienced more ion processing compared to other olivine grains in the Murchison slab may be a result of surface topography effects. The microstructure of our hydrogen-irradiated iron-rich olivine fib section looks very similar to space weather brims of Itokawa grains. Its ion-affected region is 60 to 75 nanometers thick, modeled in contrast, and characterized by few small vesicles less than 25 nanometers in length. High-resolution imagery suggests the presence of 3 microstructurally distinct zones. From top to bottom, Zone 1 is only a few nanometers thick, modeled and completely amorphous. Zone 2 is 10 to 20 nanometers thick and completely amorphous. Finally, Zone 3 makes up the bulk of the ion-affected region and is amorphous but with localized regions of polycrystallinity as indicated by the red arrows. Energy dispersive X-ray spectroscopy analysis suggests that these microstructural zones also correlate with interesting chemical trends. Most notable is the silica enrichment and magnesium and iron depletion in Zone 2, which is visible in both the elemental maps and the elemental concentration profile, which was extracted from the black arrow in the bright field STEM image at the bottom left. Keller and Berger 2014 also observed a similar silica enrichment and magnesium and iron depletion in the outermost 5 to 10 nanometers of Itokawa olivine grains. However, unlike Keller and Berger 2014, our grain's silica-rich layer is overlain by a thin, mottled, silica-depleted and iron and magnesium-enriched region. Real quickly, I'm going to go over the major takeaway from each of the analytical techniques I discussed today. XPS analyses are consistent with the removal of surface carbon and chemical reduction of iron. Veneer analyses show brightening and reddening from helium irradiation. Micro L2MS analyses suggest that helium irradiation decreases bulk organic content, while hydrogen radiation increases the abundance of certain low-mass organic free species. Finally, TEM analyses reveal ion-affected rims containing completely amorphous matrix phyllosilicates, partially amorphous and polycrystalline olivine, vesicles, and varying surface chemistry. But the major conclusion is that space weathering of carbonaceous regolith is a complex process, and there may be competing effects resulting from hydrogen versus helium solar wind irradiation and micrometeoroid bombardment versus solar wind irradiation. Thank you so much for your time.